today just going to run through a few slides showing some highlights of some of the recent work that we've been doing related to the cruise that Sverre was just talking about in the last presentation, and some of the implications and some of the things that we're looking at in the context of these volcanic rifted margin sequences for CO2 storage. Okay, so I've cut the video out of this. This is just the image. The video didn't come through very clearly on my screen last time, but basically, just as Sverre highlighted here, some of the volcanic sequences that we get, these are 55, 56 million year old lava flows, are extremely fresh and extremely open. And I guess so. One of the things we've been doing recently, this is just a paper that's I think it's now online as a couple of days ago, looking at a bit of a review of lava flows and their reservoir potential around the world. And what we find is that lava flows in particular, it's not restricted to lava flows, but this study was, can be extremely good reservoirs, can have very high porosities and permeabilities and be good reservoirs. And in other cases, they can be totally rubbish and clogged up with secondary minerals. So anybody who's been to doing field work in any of the large igneous provinces typically will have experience of seeing rocks that you really do not look like good reservoir candidates. And the full range exists, and I think this is clearly something that everybody looking at these sorts of themes has to be trying to deal with and find out where is the possibilities. And clearly we're seeing from places like Carbfix and Wallula in the States that it's viable in some areas, and so what we've been looking at is this offshore domain mid-Norway, and that's kind of what we're going to have a quick look at today. So just in terms of the research projects that we're working in, so the CO2 basalt consortia at Oslo, there's the Purbas project led by GMR, and then there's also these moratorium research grant that we were working on some of these results from the IODP 396 cruise. Just briefly, so the several of these holes, Sverre has been through them already, that targeted and recovered basaltic material. What I'm going to be focusing on today is exclusively this 1566 borehole, and so this is in the Mora margin, just very close to the transition up into the Våring, mid-Norway. And so we're going to look at some of the results in a bit more detail of these boreholes. So the first two boreholes of the cruise, small amount of granite recovery, and then this second borehole went through around about 170 meters of volcanic stratigraphy and then back into the granite at the bottom. And that's what we're going to have a look at here. The reason this is fine to put this in a talk that's linked to SDRs is that, as you can see, we have got this quite clearly defined package of seaward dipping reflectors moving towards the ocean basin here. And so we're tagging the very feather edge of this SDR package. On board, my role with colleagues was in the physical properties department, I guess you'd say. So we've got a very extensive suite of petrophysical measurements. So we've got porosities, velocities, susceptibilities, etc. And the other thing that we did was to collect mini cores from the main cores prior to them being split. So we have a suite of something like 124 mini cubes and off cores for this borehole, but then we had some additional ones from the other sites as well. So this enabled us to do some ambient permeability measurements, which I'll show just at the end of this the talk. Okay, so what does it look like? Again, if this, in terms of SDR package, I wouldn't necessarily say this was typical. This borehole has a huge range of geology. It's a fantastic borehole to work on. Everything from sorry, my screen's covered by the so we've got basically it's dominated by basaltic lava flows, and you can see this in the gamma ray sequence here. So it's very low gamma ray. This is core-based measurements, and then you've got these spikes. So these spikes in gamma ray. So for those not familiar, gamma rays, these uranium, thorium, potassium, radioactive signatures of the rocks. And these high gamma peaks here are the same as what you see at the bottom of the borehole, which is the granite, and these are sedimentary interbeds, which look like this. So these are basically siliciclastic, granite-derived sandstones and mudstones, etc., that are layered between the basaltic lava flow sequences. The basaltic lavas have got a range of facies. They go from everything from poi-hoi flows through transitional through to some of these quite clearly defined rubbly tops and bases. So we've got everything from poi-hoi through to transitional and lava flows. And again, there's quite a big range of secondary mineralization. So you go from things that are relatively unclogged and have got perhaps some clay linings through to pretty much empty, through to fully clogged units. I can maybe throw on, this is an image of some of the mini cores now. So again, you can see some of these pore systems are clogged, some of them are not. And something that we find in not all, but many lava sequences that we look at around the world is that this progression of porosity with depth is a long way from linear. It's not that porosity starts to decrease with depth and then becomes fully clogged. That happens in some cases, and there's a typical increase in secondary alteration and mineralization with depth. But there's many, many exceptions to this rule, and this borehole is no exception. Okay, but basically the pore structure is not reduced with a kind of a standard progression with depth. And this is one of the challenges that we really have to start to think about and deal with in terms of secondary mineralization and where the hydrothermal and secondary altering fluids have been. So again, beautiful range in the mini cores. Here's these nice sandstones, and you get sandstones from the sedimentary interbeds, but also this granite is very deeply weathered and actually has various sandstone stringers within that top unit. It's again interpreted as a deeply weathered granitic horizon with tores and things like this. Petrophysical data, we extremely dense amount of data that's collected on board. This is all of the offshore data that was collected. And for instance, the velocity data here shown in green, this is all discrete measurements on the core. So again, we've got a very rich database to look at some of these things, and just plotting some of the data here. This is saturated velocity versus density, saturated velocity versus porosity, etc. So we're in a strong position to look at some of the trends and the relationships between these properties and how they link to facies. And that's one of the key things that we're looking at here, is how the volcanic facies link to these physical properties, and how we can then use that to understand their reservoir properties. So this is the discrete measurements, and this is the interpretation based on the recovered core. And you can see here that the core recovery was quite high. Obviously, there's gaps where we have no core recovery, and that's where the wireline log data comes into its own. And so what we have here in this middle column is the kind of integrated volcanic facies appraisal that includes the image log and continuous wireline data compared to the core analysis. And so we've got this lithofacies summary based on the core material, and then also on this kind of finalized wireline interpretation. And you can see that, as is typical with these sequences, not all facies or components of these intrafacies are recovered equally. So oftentimes it's sediments and brecciated units that don't deliver good core, but nevertheless they're still there, and you can see them in the image log. So this is, for instance, the FMS. This is micro-resistivity image logs. So this sequence is it's composed of thin flows. So unlike these large flood basalt sequences that you see from many of the onshore analogs, and Sverre showed some of those nice examples from Iceland. In this example, we've got very thin flows typically. So we're average thickness of 3 meters here. Oftentimes they're low, so you can take that divided by 10 and add it somewhat. These are way below seismic resolution, and so this interference phenomena again is supported by this sequence. Whether this flow thickness is related to this onlapping of the lava sequence and the SDR package onto this the granitic high, or whether we've actually got evidence for proximal volcanism in here, is one of the ongoing discussions. I think I would currently put my money on there being some very localized volcanism around the Kolga high. And again, so we've got these sedimentary units that are weathering off of the granite, which is landward of this package of lava flow. So again, sediments don't flow uphill, so the sediments are clearly coming from the granitic body and flowing towards the rift zone at this time. We're very close to that sequence, so this is Again, whether it's a long distance flow towards the rift zone or more of a local phenomena is open for discussion, but certainly they're flowing to the west. And then just to
You're at the
finalize.
10-minute mark now.
Okay, super. So basically, just to finalize this would basically be my last slide. The challenge then that we have with these packages coming back from the geology to looking at more of the kind of reservoir appraisal of these sequences, we're in a good place because we've got a good amount of petrophysical and remote geophysical logs through these sequences. But you then have this challenge of how to deal with the pore structures of these lava flows and volcanic sequences, which are clearly very different from sedimentary units. And so plotted here is just some ambient permeability data against porosity, and you can see here that the flow interiors and these dark dots, as you might expect, are much lower permeability, and then in these flow tops, these diamonds, we're getting some higher permeabilities, but they're still not very high. These are talking a few tens to a few tens of millidarcies, basically. So these are not highly permeable units. We know again, the video that Sverre showed and from other analog work in the region, you can get permeabilities up to hundreds of darcies in some of these flow units. This percolation threshold of interlocking spheres can happen at quite commonly in lava flows. The recovered samples that we have here, we don't have a large amount of mini cores that we've been able to test here, but certainly it looks like the matrix-based permeability is quite restricted due to this alteration in this, at least in this borehole. The stars here are the sedimentary interbeds, and so we've got the interlava and intergranite ones, and so here we're getting better reservoir possibilities within these interlava sediments. So we've got this kind of bit of a mix and a range. How we deal with this in terms of the continuous wireline data, I'm not going to go into too many details here, but basically finding the best way to calculate the porosities and permeabilities from this sequence is complex, and maybe that's something for another place in some ways. But we clearly have quite high porosities, which are in oftentimes being linked to very low permeabilities. So there's not if I put on global data for lava flows in here, then this whole area gets filled out, and there's a whole host of different pore structures that are contributing to this. And we can only measure matrix permeabilities in the lab easily. You can't take mini cores out of fractures, and clearly through volcanic sequences and lava flows especially, the presence and the distribution of fractures is critical for oftentimes the effectiveness of working reservoirs. And so this ways in which we deal with this, again, I'm just throwing on a couple of published models here just to show that there's this very wide range in terms of how, what model is most appropriate, which one should you choose. Probably none are going to fit everything, but then you have to come up with your best approaches. So I think in some ways I'll leave it there. They're complex reservoir units. They have certainly have potential in some areas, and in other areas they appear to be fully clogged. That's part of ongoing work, and is a big challenge for all of those working in this area. So then just to finish, this borehole in particular was quite an exciting one for mid-Norway. It was the first well to prove the nature of the sub-basalt sequence. Turned out to be, in this case, granites with sedimentary stringers, etc. It was the first well to penetrate the base of an SER package in the North Atlantic, maybe globally as well, as far as I'm aware. First proof of siliciclastic interlava sediments offshore Norway. Again, this has quite implications for reservoir potential. If you go south down the margin, then sedimentary interbeds similar to this host important hydrocarbon reservoirs to the south in the Faroe Shetland Basin. We have this northwest sedimentation of the sands that are being weathered off of the granite towards the rift zone, at least locally. And then just the reservoir appraisal of these basement lavas and interbeds is part of this ongoing CCS appraisal for the North Atlantic. And there's still a lot there's a lot of variation to deal with, and that means that we've still got a lot of work to do to know the scale that this can or could be deployed at. So yeah, thanks for listening.
Brilliant. Thank you so much, John. If anybody has any questions, please raise your hand or put something in the chat. in the interim, I don't know if you'll know the answer to this, but it seems to me that fracking is going to need to be a thing if there's going to be carbon storage in these kinds of deposits. But they're super tricky because they're so heterogeneous in terms of the layering. Have people managed to frack such complex heterogeneous formations successfully, and does it not introduce horrific challenges?
Yeah, no, it's a good question. I'm not sure certainly in some cases that would be the only option. In many others, I don't necessarily think it's always required. For instance, the Deccan traps, there's a field called the Rageshwari deep gas field, which they frack for natural gas, and that's again it's a tight reservoir composed of Deccan lava flows, and there's also some more evolved ignimbrites and things, but they have an extensive history of managing that reservoir for natural gas extraction using fracking. So it can be done, and I know that as part of that, then certainly the in situ strength and stress state of the reservoir is critical for trying to design those sorts of programs. But yeah, I think yeah, that's certainly it certainly has been done. Where obviously that brings the question about where it should be done and where it's viable to be done, because of course you can't do that everywhere for sure. But yeah, it certainly has been done, and there's a bit of research on it.
Brilliant. Thank you. There's a question, or Vanalta him has his hand up. Can you unmute and ask your question, Vanalta?
Yeah, sure. Sorry, it's me again. I have a question for the last two speakers about this IODP expedition, which I'm very interested in. You've shown here that you have sedimentary intervals, and I'm very much interested in those. And you've shown on your log, you have approximately, let's say, 10-20% of sediments. And I've worked in the Danakil Depression, and there I have seismics, and I also see seawall dipping reflectors on my seismic. But when I go on the field, I see a majority of sediments and a minority of lavas. So I would like to know whether in other cores you found more sediments, or if therefore the Danakil is maybe something very special.
Yeah, I mean it's I don't think there's any rules. So in that sense, it's I mean reflectivity is what you're seeing. So then I think a lot of it comes down to the proximity of the sediment source and the nature of it. So again, in this particular borehole, we were very close to a granite which was washing off, weathering and giving these sediments. In the other boreholes we drilled further north, clearly there was no source for siliciclastic sediment, so it was only volcaniclastic sediments. In those cases, we got some thin ones, but they were certainly less well developed than we see here. If you're in a regime that has a lower volcanic output, I think this is what it comes down to, isn't it? Is that it's an interplay between sedimentation and volcanism. Being a bit biased, I kind of like scenarios where volcanics have won, but they don't. They're not the only. They're not the only setting for sure. So if you have periodic minor volcanism, then no reason to suggest you couldn't have a sediment-dominated system.
Thank you.